Hello students, let's begin Lesson 2. Lesson 2 and Lesson 3 will cover Chapter 2 of our textbook, Probability. Now, what is this probability? We had been using it a lot, but what does it mean? Well, if we are to answer that question, we need some terminologies, so that's where we're going to begin. First, the sample space. A sample space is a set of all possible outcomes of an experiment. Alright, is that clear? Is that clear? Well, I don't know about that. I mean, what do you mean by an outcome? And what is an experiment? This is not good. Instead of answering a question, I ended up bringing a couple more questions. But then again, at least, the first question is not too bad, so let's think about that. An outcome must be something that's coming out of the experiment. It's an output. So it's an output of a function called an experiment. Okay, that's a well understood concept, output of a function. But then again, what is this function called an experiment in that case? Well, there goes another question. According to our textbook, an experiment is an activity subject to uncertainty. Great. Is that clear now? Is that clear? Come on, what do you mean by clear? This is worse, clearly worse than before. What is an activity? And what do you mean by so-called this uncertainty? Clearly, it's not working out. Instead of answering a question, I ended up bringing a couple more questions. And from there, a couple more questions. And on and on and on. That's not going to end. And each time I end up getting a question that is even harder to answer. Clearly, this is not working out. As a matter of fact, this is always the case, really, without exception, always the case whenever anybody tries to clarify everything. It's impossible. It's always like that in mathematics. Math is not built that way. You have to draw a line somewhere. Here in this case, I'm going to draw a line right here, experiment. I'm not going to make any kind of efforts to define or describe what an experiment is mathematically. Instead, I'll just accept it as an English language with the dictionary meaning and go from there. So, given an experiment, I'll consider all possible outcomes and put them all together and form a set. And that set is going to be called the sample space. Wait a minute. Did I say a set? Formed a set? Oh, that's great. That's really good because finally we ended up with a well-understood mathematical concept. A set. Something everybody is familiar with. We all know about that, and we have been studying about it from elementary school days. So that's where I'm going to begin. A sample space is a set. It has to be a non-empty set because if there's nothing in there, then I cannot do any kind of mathematics with it. So it's a non-empty set. Therefore, there are some elements in there. And I'm going to name those elements as the outcomes. So, alright, sample set, that's a set. And elements, outcomes. So, what's the next aspect of a set theory? A subset. And a subset is going to be called an event. And we use this kind of notation. An event E is a subset of S. Or vice versa. A subset of S is called an event. I believe everybody is familiar with this expression here from elementary school days. But another way to express the same thing is to use the power set notation like this. E is a member of the power set. This expression here, which everybody is familiar with, and this expression here, which is a little bit more intimidating, actually mean the same thing. And this expression, P of S, is a power set, and it's a set of all subsets of S. So anything belongs to this power set means it's a subset. So this expression here and that expression there actually are the same thing. It's just that this one here is usually more complicated, so usually better avoided. But in some cases, it is more convenient to consider this one instead of the other way around. And we're going to see this example pretty soon, actually, from the very next subsection, and then way back down here, subsection 1.7. Okay, so much for the notation issue, and here are some more discussion about the events. If an event has only one outcome, then it is called a simple event. More than one outcomes, then that event is called a compound event, I think. That's not really important. Okay, next. Now this one is really important. Everybody should remember this. A pair of events A and B are called mutually exclusive if the intersection is empty. No overlap. Empty intersection. And here is a visualization. No overlap. Mutually exclusive. Next. A pair of events A and B are called complement events if they are, number one, mutually exclusive, no overlap, and also their union covers entire sample space. Here's a visualization. So no overlap, they're mutually exclusive, but also taking a union, it covers everything. Previously here, mutually exclusive, yes, no overlap, but they do not cover everything. There are plenty of white parts here. In general, here, no, covered everything. In this case, we call these complement events. So B is complement of A is complement of B. So mutually exclusive, and also the union covers everything. Okay, I guess we covered all the necessary lingos, and now let's go over to the axioms of probability. Ready? Alright. Let S be a non-empty set, which we'll call the sample space. Furthermore, we'll call the elements and the subsets of S the outcomes and events, respectively. Now, a probability on S is a set function defined for all events that satisfies these three axioms. Number one, for any event, the probability of that event is between 0 and 1. Greater than or equal to 0, and less than or equal to 1. Yes, equality is possible. Next, the probability of an empty event is 0, and the probability of the entire sample space is 1. The total is 100%. Nothing exceeds that. Now finally, number 3. If you have a string of mutually exclusive subsets, A1, A2, A3, A4, A5, and so on, possibly infinitely many, then the probability of that mutually exclusive union is the same as the sum of the probabilities. It works not just for 2, 3, 4, or 50,000, but also infinitely many as well, when we have an infinite sequence of mutually disjoint sets. This expression here, with union plus, is called a disjoint union, and that's a shorthand of a union where each pair is mutually exclusive. Our textbook author does not use this union plus notation. He just uses usual union symbol. And whenever we have mutually exclusive events, then we write this kind of thing, pairwise mutually exclusive like this. But I got kind of tired of specifying all of these whenever they are necessary, so I'm going to use a simple expression like this. Whenever you see this union plus notation, then you have to assume that this goes without saying. Here's an explanation, or here's an example. Consider this brown set and blue set, 1, 2, 3 versus 4, 5. And take the union, so we have 1, 2, 3, 4, 5. No overlap, no intersection, so this is a disjoint union or mutually exclusive union. You can use union plus. Down here you can't, because we have non-trivial intersection. 3 is common, so you cannot use union plus there, that will be wrong. Of course you can use usual union here as well, that's not bad. In this case, that's not cause any kind of confusion because you can see 1, 2, 3 verse 4, 5. Clearly you can see that. But if those sets are not specified, you have a bunch of characters. In that case, you have to specify this or something equivalent if you mean disjoint union. Or, of course, you can use union plus. Alright, so much for the axioms of probability. And we didn't completely finish 1.2. There are some more comments here and there, but that's something I'm going to come back and discuss in separate video. I don't want to get too deeply right now at this moment. So for now, let's just keep it at that, and let's go to an example problem here. When the sample space is a finite space, then the probability and the relative frequency satisfies these 3 axioms, so it works as a probability. So the relative frequency, let me expand the font, the number of elements over number of elements simply by counting. So number of elements of event A over number of elements of the entire sample space S. So denominator is bigger, certainly. So we have to have this greater than or equal to 0, less than or equal to 1. And now, if A is an empty set, then no elements there, so we're going to have this. Great. And A is equal to the sample space S. In that case, numerator and denominator are the same, so fraction is 1. And finally, this one, yeah, you can check those because we are talking about the same denominator, and then numerator is just number of elements. So yeah, the addition rule applies. So you can easily check all those. And as for a little bit more concrete example, here's one. Roll a pair of fair dice, and then here's a sample space. We have 1, 1, all the way to 6, 6. And there are total 36 outcomes. So that goes to denominator. Let's answer some further questions. What is the probability that the total number of dots showing is at least 10? At least 10, so 10, 11, or 12. So these, in top right hand side corner, and then add them all up, there are 6 out of 36, and there goes the probability. Easy computation. How about more than 10? So 11 or 12, not 10, 11 or 12, so only these 3, so we have 3 out of 36. Next question, at most 10. So 10 is included, 10 or less, 2, 3, 4, 5, 6, 7, 8, 9, or 10. So all these down here, if you count them up, you're going to get 33. Oh, excuse me, wrong cell. 33 out of 36. And by the way, consider this, and then the answer for part C. And please note that these are complement events. Greater than 10, so 11 or 12, versus less than or equal to 10, 2, 3, 4, 5, 6, 7, 8, 9, or 10. Mutually exclusive, and then together they cover everything, so they are complement events. So if I add up the probability, I can straight add those up because they are mutually disjoint. And then I'm going to get the union, which is the sample space. Not coincidentally, 1 plus 11 12th is 1. Yep. Add up to the whole probability of 1. Similar thing goes to at least 10 versus less than 10. They are complement events. And then the probability add up to 1. You can easily see those. Alright, so much for this elementary example about counting. So relative frequency is an example of a probability. It works well in a finite sample space. How about an infinite sample space? In that case, the counting is totally meaningless, and instead you have to rely upon appropriate measurement. So if it is one-dimensional, then length will do. Two-dimension, area. Three-dimension, volume, like those. And then if you have finite sample space, then actually those are zero-dimensional. In that case, counting is actually the measurement associated to zero-dimensional cases. Similarly, it goes like this: measurement of the event over the measurement of the entire sample space. So that kind of thing works as a probability, and people call it probability measure. Previously, for counting, the probability for the usual probability for finite sample space on counting is called relative frequency over the total. And this one is typically called probability measure. And here's an example of a probability measure for a two-dimensional case. Randomly thrown dot hits the circular dartboard. If it goes out of bound, then it's out of consideration. So the total of the sample space is the disk only. Now, what is the probability that dot hits the inside of the square region? Pictured as follows. It's just random, not being aimed or anything like that. So it's going to be area over area. And here's the computation. And area of this entire sample space, pi r squared, is easy to see. It's a circle. Radius is r. But then again, the radius of the square, is it 2r squared, as I claimed here? That's left to the students. Indeed, it'll turn out to be 2r squared. Think about it. So that after cancellation, you have 2 over pi, which is kind of like this. So it is possible to consider all kinds of probabilities for counting in finite sample space with relative frequency. For infinite cases, it has something to do with the natural measurements and then dimension. Next topic, complement and odd. So complement probability, yeah, we discussed those before. We had complement events and the probabilities added up to 1. As a matter of fact, you can actually prove that. You see, what is the probability of entire sample space? That's probability of A union. Oops, I should have got it open. Union, where is union? Union plus, okay. And A complement. And that's probability of A plus probability of A complement. Because they are disjoint, then I can add up the probabilities. You see, it's coming from the third row here. But then again, what is the probability of the whole space? That's 1, isn't it? So probability of A complement is flipping this P of A to the other side, 1 minus probability of A. So here goes a full proof actually. So yes, you can get complement probability and odds in favor versus odd against, well, probability of A to probability of A complement. Here's an example. You have 2 blue balls and the other 3, and if you have a blue ball, then you win $1, otherwise you lose $1. So there are 2 winning balls and 3 losing balls. So what's the odds? In favor? Clearly 2 to 3. Everybody can do that. 2/5 or 3/5. Odds against 3 to 2. Come on, that's too simple. Not really worthy of 3000 level course. Alright, so much for section 1.